All right. Basically, um, we are going to be beginning our exam focus class. If you can hear me, can you just indicate? Can you just indicate that you can hear me? All right. Indicate that you can hear me. You can just type in the comment box below that I can hear you, sir. All right. So basically, in this class, we'll be looking at a couple of topics. Basically, exam focus. I would like you to tune in. Keep tuning in till the end of the class. All right. It's going to be really helpful. All right. So it's chemistry exam focus, and then we are going to be focusing on a couple of topics. All right. Topics like significant figures, then look at the mole concept and Avogadro's number. We'll look at calculation involving formula mass. Okay, so we'll be looking at the periodic table as well. Okay, we'll look at chemical bonding and all of that. So I would like you to be glued to this class. All right. Okay. So we'll start with significant. We'll start with significant figures. All right. So basically, what are significant figures? Significant figures refers to the number of important single digits in a number expression. All right. Important single digits, from the word significant. Keyword there, important. All right. So the number of important single digits, all right, that are present in a number expression. When I say single digits, I'm talking about numbers from 0, 1, 2, 3, 4, 5, 6, 5, 6, 7, 8, 9. These are single digit numbers. From 0 to 9 are called single digits. All right. So the number of single digits that are important, all right, in a number expression, are the things we refer to as significant figures. All right, are the things we refer to as significant figures. Okay, so there are rules for naming significant figures. Significant figures have rules, very crucial rules that must be followed. All right, now I will be running through these rules and I will give examples of each of these rules. All right, so you will be able to understand it better. Now, number one, all non-zero digits are significant. All non-zero digits are significant. That's number one thing you must take note of. That is, every digit that do not have zero, that is not zero. First of all, every digit, all non-zero digits from 1 to 9 are significant. There is nothing that is arguable about it. From 1 to 9, they are all significant, as long as it's not zero. Although there are cases where zero can be significant, but there is no case where numbers from 1 to 9 are not significant. So for instance, now if we have something like, let's say we have 32.2 meters, if you look at this value, have three values that are not zero, so it means that we have three significant figures here. Okay, so sorry for that break in transmission. So as I was saying, we are calculating for nitrogen. So nitrogen here, so this will be 1 times 14, 14. So 14 over 123, 14 over 123 times 100. Okay, times 100. So 14 divided by 123, 123. Okay, multiplied by 100. Okay, so that's going to give us 11.38. All right, so this will give us 11.38%. All right, then the last element here, the last element in this compound is oxygen. So now let's calculate. So oxygen in C6H5NO2. Oxygen has how many atoms of oxygen are here? Two atoms of oxygen. What's the molar mass of oxygen? Oxygen is 16, so divided by 123. Remember, we'll always use this 123 because it's the relative molecular mass of the compound. All right, so 2 times 16 is 32. So 32 over 123 times 100 times 100. So we say 32 divided by 123. This will give us 0.26. When we multiply it by 100, we're going to get about 26%. So this is 26%. All right, or 26.02%, as the case may be. So basically, now the idea now is that when we add all of these percentages, it's supposed to give us 100. So now let's check if we have 100. The first one we got 58.54. So 58.54. Carbon gave us 58.54%. Hydrogen gave us 4.07%. Nitrogen gave us 11.38%. And oxygen gave us 26.02, or just 26%. So when we add everything, you can see we are having what? 100.01%, which is still 100%. All right, so the sum of all of this, if you want to know if you're actually correct, the sum of all of this must give you 100%. It's very, very crucial that it gives you 100%. So that's percentage composition of a compound. That's how we solve for percentage composition of a compound. All right, so the next thing we'll be looking at will be empirical and molecular formula. So we're looking at empirical and molecular formula. Empirical and molecular formula. Okay, so that's the next thing we'll be looking at. All right, so what is empirical formula? Empirical formula is defined as the simplest formula of a compound, which shows the exact simplest mole ratio of the constituent elements in the compound. So it shows, empirical formula shows the simplest mole ratio. All right, the simplest mole ratio, while molecular formula shows the exact number of moles of the constituent elements. Sometimes we call constituent elements atoms in the compound. All right, so basically, we won't talk too much. Let's just go straight into a question. So the first question here says what is the empirical formula? What is the empirical formula of L-dopa? L-dopa, a drug used for the treatment of Parkinson's disease. All right, if it has the following compositions, and the compositions are 54.82% carbon, then hydrogen, 7.10% nitrogen, and 32.46% oxygen. Question mark, but it's a question. Now, as you can see, hydrogen, I don't want you to be confused. Hydrogen is not given. So this is for carbon, this is for nitrogen, and this for oxygen. The percentage composition of hydrogen is not given. All right. Remember, I told you that these percentage compositions are actually called percentage by mass. So the same way you use masses, the same way you use mass to solve, it's also the same way you should use percentage. All right, percentage compositions. Okay, so this is actually a question before us. So now, in order to solve this, we have to state our parameters first. Now, carbon is 54.82%, right? Nitrogen is 7.10%. Okay, oxygen is 32.46%. Now, how do we get that of hydrogen? It's very simple. For hydrogen, now remember that I told you that the sum of the percentage composition of elements in a compound must all be equal to 0. So which means that how to get that of hydrogen, since we have the other ones, we say 100 minus, then we add all of these, 54.82 plus 7.10 plus 32.46%. we'll add all of this. All right, so this will be 100 minus, let's do it together. So we have 54.82 plus 7.10, then plus 32.46. So when we add all of this, we are getting 94.38. all right, 94.38. So we have 100 minus 94.38. so if we do 100 minus 94.38, going to be getting 5.62. so it means that hydrogen is equals to 5.62%. so this is the percentage of hydrogen. All right, so basically if you're given the percentage composition of all other elements except one, just say 100 minus, then add those elements, subtract it from 100, you'll now get the percentage of the unknown. You do that, you have to do that before you start solving, okay, because you cannot proceed with solving if you don't know the percentage composition or percentage by mass of all the elements. You need to know. One doesn't have to be unknown, they all have to be known. All right, it's very crucial. Okay, so it's very important to note that. So now the next thing we have to do, create a table like this. All right, create something like this. Now here, okay, you write the different steps of your calculation. You write the different steps of your calculation here. All right, so you can write steps at the top. Okay, then write the different elements. We have carbon, we have hydrogen, we have nitrogen, and we have oxygen. Just do it like this. All right, and draw a line like this. Now what are the steps? The first step now is to actually calculate the number of moles. All right, so the first step is to calculate number of moles. So the formula for number of moles is mass over molar mass. That's the first thing. Calculate the number of moles of each of these elements. So I told you that this percentage by mass is the same thing as the normal mass, even if it's not expressed in grams. You don't have to convert anything, just take the exact values as they are. All right, so what do I mean now for carbon? Now the percentage by mass for carbon is 54.82. now divide it by the molar mass. The molar mass of carbon, okay, is 12. Carbon is 12. All right, in fact you are even supposed to have it in the question now. C equals to 12, nitrogen is equals to 14, hydrogen is equals to 1, oxygen is equals to 16. But you just have to be familiar with these things, so you don't necessarily have to wait until you see it being added to a question. Just be familiar with the mass number of the common elements. All right, then now let's move forward. Let's look at hydrogen. Hydrogen has a percentage by mass of 5.62. so 5.62 divided by 1. Nitrogen is 7.10. molar mass of nitrogen is 14. Oxygen is 32.46. that is what we are given. So divide it by what? 16. All right, then you solve. So now let's do it individually. So the first one, 54.82 divided by 12. So this will give us 4.568. all right, so we have 4.568 mole. Okay, 4.568. be very careful with approximation. If you have long values, it's safe to just leave it in 3 decimal places. Then 5.62 divided by 1 is still 5.62 mole. It's still 5.62 mole. 7.10 divided by 14. 7.10 divided by 14. So this will give you 0.507. 0.507 mole. All right, then the next one is 32.46. 32.46 divided by 16. So this will give you 2.02875, 2.02875 mole. Okay, 2.02875 mole. So these are the moles. So this is step one. Now the next step now is to divide by smallest mole. Divide everything here by the smallest mole. So what's the smallest value here? The smallest value here is clearly 0.507. So we say 4.568 rather divided by 0.507, 5.62 divided by 0.507, 0.507 divided by itself 0.507, 2.02875 divided by 0.507. So now, of course, this one will be 1 because anything divided by itself is 1. So let's do the rest. 4.568 divided by 0.507. When we divide this, we'll have 9. We'll have 9. Okay. 5.62. 5.62. Remember that you need to have whole number ratios. It must be whole number, not decimal. So you have to round it up to the nearest whole number. 5.62 divided by 0.507. So you have 11.08, which is still 11. All right. Then the last one, we have 2.02875 divided by 0.507. So this will give us 4.00. That is 4. Okay, so it is from these ratios, these whole number ratios. Okay, remember I told you that the simplest whole number ratios, okay, is what gives us the empirical formula of a compound. So it means that the empirical formula will be empirical formula. It means empirical formula would be C. If you look at C9, hydrogen is next, H11, nitrogen is next, N, then O4. So this is the empirical formula of the compound. All right, so it's very important for you to know how to calculate empirical formula, and if you follow these steps that I just explained to you now, it will be very, very easy and very seamless to actually calculate the empirical formula of a compound. All right, so that's it. Okay, that's it. So I'm giving you an exercise that I want you to try. Okay, so you can just take this down. I will dictate it. What is the empirical formula? What is the empirical formula of a compound? What is the empirical formula of a compound that contains 0.783 grams of carbon, 0.783 grams of carbon, 0.196 grams of hydrogen, 0.196 grams of hydrogen, and 0.521 grams of oxygen. All right, so it contains 0.783 grams of carbon, 0.196 grams of hydrogen, 0.521 grams of oxygen, and of course C, remember C is equals to 12, H is equals to 1, and O is equals to 16. All right, so I want you to try this quickly. So try it, and you can write your answer in the comment box below. So I'm going to give you a little time, about let's say 2 minutes, to try it out. All right. All right, so we are back. So the next thing now we'll be looking at exercises on molecular formulas. All right, on molecular formula. So remember what I said about molecular formula. It shows the exact or actual number of atoms, okay, or actual number of atoms of each element present in a molecule or compound. So it is exact. All right, it is exact. It's exact. So how do we determine molecular formula? So molecular formula is equals to empirical formula. Let me use F, then N outside. So what is N? N is called whole number multiple. Whole number multiple. And the formula is molecular weight. Molecular weight. Remember, molecular weight is also called relative molecular mass. All right. So molecular weight all over formula weight. Formula weight. Formula weight is the empirical formula weight, EFW. So formula weight is more like the molecular mass of your empirical formula. All right. So quickly we'll be looking at a question where we can be able to solve molecular formula. All right. So now let's quickly do that. So now let me write down a question. Okay. So now a compound has the following composition by mass. Now C is equals to 0.681 grams, H is equals to 0.137 grams, and O is equals to 0.181 grams. Now A, calculate the empirical formula of the compound. Calculate the empirical formula of the compound. Then B, if the relative molecular mass of the compound is 88.17. Now calculate the molecular formula. All right, calculate the molecular formula. Okay, so the first thing we are going to do is to calculate the empirical formula of the compound. Then secondly, we calculate the molecular formula. At least we now know how to calculate empirical formula, so it will not be difficult. But you cannot calculate molecular formula if you have not known the empirical formula of the compound. So it's important for you to actually know the empirical formula of the compound before you go ahead to calculate the molecular formula of the compound. All right, so now let's dive straight into that. So remember what we did the other time. I told you create tables like this. Now this side will have to do with the steps. So you say steps here. Then the three elements are carbon, hydrogen, and oxygen. All right, then you draw your horizontal line. Now the first thing I told you is to calculate the number of moles. And I told you that moles is mass over molar mass. What's the mass here? Mass of carbon is 0.681. Molar mass of carbon is 12. Mass of hydrogen here is 0.137. If you look at, they use actual masses here. In the previous exercise we solved, they used percentage by mass, and I told you that they are the same thing. All right, so if you're giving percentage by mass, just use it and divide by the molar mass. If you're giving mass, just use it as well. All right, so then 0.181 divided by the oxygen is 16, right? Okay, so now let's calculate this. So we have 0.681 divided by 12. So when we divide this, we are going to have 0.05675. 0.05675. Okay, then 0.137 divided by 1 is still 0.137. Then remember, all these things are moles. So now let's write it mole. So 0.181 divided by 16. All right, so this will give us 0.0113 mole. Okay, then the next thing now is to divide by smallest mole. What is the smallest mole here? The smallest mole is obviously this guy, 0.0113. So divide each of these values by, so 0.05675 divided by 0.0113, 0.137 divided by 0.0113, 0.0113 divided by 0.0113. Okay, so now let's do that together. So now let's divide this first value first. 0.05675 divided by 0.0113. So when we divide this guy now, we'll have 5. We'll just have 5 because these are simple whole number ratios. Then 0.137 divided by 0.0113. 0.0113. So this will give us 12.1, which is still 12. This is 12. Then this will give us 1. So it means that our empirical formula here is C5H12O. C5H12O. Alright? C5H12O. So as you can see now, it's clearly our empirical formula. So now how do we now go ahead to calculate the molecular formula? Simple. I told you that molecular formula is equals to empirical formula then N. And what is N? N is relative molecular mass divided by formula mass. So in this question now, remember, we are giving relative molecular mass to be 88.17. So you say 88.17. The formula mass is the molar mass of the empirical formula. So how do we do that? We calculate it like this. Say 12 times 5 plus 1 times 12, then plus 16. Remember how we calculated molecular mass now initially? It's still the same way. All right, so this is 88.17 divided by, let's calculate 12 times 5. 12 times 5 plus 1 times 12 is 12, then plus 16. So this will give us 88. All right, so this will give us 88. So 88.17 divided by 88 will give us 1. All right, give us 1. So it means that our molecular formula now will be equal to, empirical formula is what? C5H12O, then 1. Now any number you see here is what will multiply inside. If this guy were to be 2, carbon will be 10, hydrogen will be 24, oxygen will be 2. So your n now, the aim of getting your n is to multiply into your empirical formula. So now it means that 1 times 5 will still give us 5. 1 times 12 will still give us 12. 1 times 1, oxygen is 1 here, will still give us 1. So it's possible for your empirical formula to be the same as your molecular formula. And the only time when it's possible is when your n gives you 1. Gives you 1. Now I want to let you know of a trick as well. Okay, sometimes they will not give you relative molecular mass, all right, but they will give you vapor density. Vapor density is denoted as VD. So if they give you vapor density, relative molecular mass, how do you get relative molecular mass? Relative molecular mass is 2 times vapor density. So let's imagine now they give you vapor density as, let's say, 24. It means that relative molecular mass now will be 2 times 24, which will give you what? 48. So this is what you now use in solving when you get to this point after you've calculated your empirical formula. That is when you're giving vapor density. But if they give you relative molecular mass direct, just use it straight, just like we have here. We just use this straight and we solved. All right, and we solved. So basically, so that's it basically. All right, so so that's the idea. Okay, I would want you to try and search for other exercises. Any exercise you see that has to do with empirical molecular formula. The best way to actually get used to anything you learn is by practicing. All right, is by practicing. Okay, but then I want you to actually learn a different type of empirical molecular formula exercise. All right, this one is a little bit complex. All right, this one is a little bit, it's slightly complex, okay, but it's something you can understand. So this is actually empirical and molecular formula, or empirical formula, using the composition by mass from combustion. What is combustion? Combustion is actually when a compound burns completely in the presence of oxygen gas to form carbon dioxide and water only. All right, so basically I'm going to be giving you a question now. I'm going to be giving you a question. So we'll solve it together actually. Okay. But like I said, this one is you solving for empirical formula, and you're not giving the mass of the elements or percentage by mass. Rather, what you're giving here is the mass of the products that are formed during combustion. Combustion is, for instance, now, if we have an organic compound, so combustion is basically that organic compound, okay, that organic compound. Let's say the organic compound is A plus oxygen gas to produce carbon dioxide and water, okay, and water. So usually we have CXHY plus Y plus X plus Y over 4 O2 to give us XCO2 plus Y over 2 H2O, Y over 2 H2O. This is called combustion formula, but it's not what we are going to use. Oh, but just bear this in mind. You may come across this much later. All right, but just bear this in mind, okay. But now, one thing that is very very crucial now is this particular question I told you about. Now, it looks simple, and it's also simple. All right, it's simple when you've been able to learn it. All right, so that's why we are going to solve it now. So let me just write down the question. Okay, so you can write as I'm writing as well. Okay, so the question goes this way. Say an organic compound A contains only carbon, hydrogen, and oxygen. Okay, full stop. So when 1.46 grams of A bonds in excess oxygen, 2.79 grams CO2 and 1.71 grams H2O are formed. All right, so carbon is equals to 12, hydrogen is equals to 1. So now, but the question is this: A, calculate the empirical formula. Calculate the empirical formula of A. Then B, if the relative molecular mass of A is 92.16, what is the molecular formula? What is the molecular formula? All right. So, what is the molecular formula? So basically, we are going to be solving this exercise right away. All right. So let's flip. Okay, I would like you to just take a minute to write down this question, so I can just flip the page on a blank sheet, so we'll solve it together. All right. So let me give you just 2 minutes to solve this. Not to solve it, to write down the question. Not to solve. We'll solve it together. Don't be scared. All right. So let's solve it now. Let's solve it right away. Okay. So I believe you've written down the question. Now, if you look at it very well, okay, let's just list the parameters that we're given. Okay. So let's say solution. Let's say solution. Now, we are being told that we are being told that an organic compound A, all right, bond completely in the presence of oxygen gas and carbon dioxide and water were formed. This is a typical combustion reaction, and we are being told to determine both empirical and molecular formula of A. Now, how do we do this? Now, you also remember that in the question they said that when this combustion was done, see 2.79 grams of CO2 and 1.71 grams of water were formed. But you remember that if we have to calculate empirical formula, we need the mass of carbon, we need the mass of oxygen, we need the mass of hydrogen, or at least bad as bad, percentage by mass. But in this case, rather than having the mass of carbon, oxygen, and hydrogen, we are having the mass of a compound and another compound, carbon dioxide and water. How do we navigate through this? Now, it's simple. All right, it's simple. So basically, there is a very simple strategy to this for us to get the mass of each of them. Now let me give you mass of carbon now, mass of C. To calculate the mass of C now, we say this C, okay, say molar mass of C, molar mass of C divided by molar mass of CO2, okay, then times mass of CO2. Divide the molar mass of the element in the compound, all right, divide it by the molar mass of the compound itself, or we say it's best to say this way: n times molar mass of C, n times molar mass of C divided by molar mass of CO2, then there is mass of CO2. Look at what I mean. How many atoms? Remember, anytime we say n, how many atoms of carbon do we have here? 1. So we say 1 times molar mass. This is almost similar to percentage composition. The only thing is that we are not multiplying it by 100, all right, but it is still n times molar mass of C. What is the molar mass of carbon? 12, right? Divided by, what is the molar mass of carbon dioxide? 12 plus 16 times 2. Then times, what is the mass of carbon dioxide given? 2.79. So what would this be equal to? This would be equal to 12 over 16 times 2 is 32. 32 plus 12 is 44. All right. Remember, these are in grams per mole. Grams per mole. Then multiply by 2.79 grams. Gram per mole cancel gram per mole. This would be equal to, let's calculate it. So we have 12 divided by 44. This will give us 0.2727. When we multiply it by 2.79, so our answer will be 0.76 grams of carbon. So it means that this is the actual mass now we're using solving for carbon. This is how to do it. Like I said, multiply the number of atoms by the molar mass of that element and divide it by the molar mass of the compound. Then multiply it by the mass of the compound that you were actually given in the question. All right. So that's the strategy. So we have done for carbon. Let's do for hydrogen. So mass of hydrogen, mass of H. Whenever you do for carbon, the next thing you should do for is hydrogen. Now, so n times molar mass of H divided by molar mass of water. The reason why we are using water is because it is water. It's inside water that we have hydrogen. We don't have hydrogen inside carbon dioxide. We have hydrogen inside water. All right. So, what is the molar mass of? Okay, first of all, in water, in water, how many atoms of hydrogen are in water? We have 2. Okay, so 2 times 1 gram per mole. Remember, the molar mass of hydrogen is 1, so divided by, what is the molar mass? Okay, remember, we are supposed to multiply now. Mind you, let's not forget, we're supposed to multiply by the mass of water. So when we divide this, we are supposed to multiply by mass of water. Don't forget that. All right, so let me bring this down. So 2 times 1 grams per mole divided by, what is the molar mass of water? Water is 1 times 2 plus 16. So this will give us 2 grams per mole divided by 2 plus 16 will give us 18 grams per mole. Then we'll multiply by, what is the mass of water that we are given in the question? We are given 1.71 grams. Gram per mole cancel gram per mole. So let's calculate. So we have 2 divided by 81. Sorry, 2 divided by 18. Well, then we multiply it by 1.71. All right, so our answer is going to be 0.19 grams of hydrogen. All right, 0.19 grams of hydrogen. So we have gotten that of hydrogen. We have also gotten that of carbon. Now the next one is for oxygen. Now, if you've gotten for carbon and hydrogen, the next one for oxygen, how do you do that? Remember that let's refer back to the question. Okay, all right. Remember, it says when 1.46 grams of A bonds, which means that now this is the mass of A. This is the mass of A that was given. So it means that inside this 1.46 grams, we have the mass of carbon, we have the mass of hydrogen, and we have the mass of oxygen. So inside this 1.46 grams, we have the mass of carbon, we have the mass of oxygen, hydrogen, and we have the mass of oxygen. So now look at what I'm saying. We are saying that see what I'm saying here. What I'm saying is that mass of A is equals to mass of carbon plus mass of hydrogen, then plus mass of oxygen. So in order for us to, so what is the mass of A now? Before I say what I want to say, what is the mass of A? Mass of A in the question is what? Mass of A in the question is 1.46 grams. So we say what? 1.46 grams equals to, what is the mass of carbon when we calculated? 0.76 grams. What is the mass of hydrogen? 0.19 grams. What is the mass of oxygen? Unknown. Let's call it X. So it means that for us to get mass of oxygen, so we'll move these guys over. So it means that mass of oxygen, which I wrote as X, but let me even write it in full. Mass of oxygen, since it's unknown. So mass of oxygen will now be equals to 1.46 minus, if 0.76 goes over, it will minus 0.76. If this goes over, it will minus 0.19. So what do? We say 1.46 minus 0.76 minus 0.19. Sorry. Let me solve it again. 1.46 minus 0.76 minus 0.19. So this will give us 0.51. All right. So this will give us 0.51. So it means that the mass of oxygen is 0.51 grams. Are you seeing how easy it is? So basically, when you get for carbon and hydrogen, use the mass of the compounds now to get the mass of O. Just substitute. Mass of A is supposed to be mass of C plus mass of H plus mass of O. That is that, because the organic compound should contain carbon, hydrogen, and oxygen before it can combust. All right, CHO, before it can combust. So that's something that is very, very crucial for you to know. So now that we have gotten the mass of oxygen, carbon, and this thing, we can now solve like we've been solving before. So this is the only thing now that differentiates what we were doing before from this. Okay, so you have to now calculate the mass, get the mass of each of the elements before you now start. Remember when we want to do empirical formula, I've been telling you this. We have to draw our lines like this. Here we'll show the steps, then we'll not pick each of the elements. Carbon, next one hydrogen, the next one oxygen, then we'll draw. So now the first step is number of moles. Don't forget that. What is the mass of carbon here? The mass of carbon that we calculated was 0.76. Look at it here. Look at it. What is the mass of carbon? 0.76. So we say 0.76 divided by molar mass of carbon is 12. Okay. All right. Mass of hydrogen is 0.19. Molar mass of hydrogen is 1. Mass of oxygen is what? Mass of oxygen we calculated 0.51. Molar mass is what? 16. All right, so let's solve them individually. So if we do 0.76 divided by 12, we should be getting 0.063. This will be 0.19. Then 0.51 divided by 16. All right, when we divide, so this will give us 0.03. All right, 0.03, 0.031875. Let's just take all the values. 0.031875. all right. So now what do we do next? Remember, all of these are in moles. So what do we do next? We divide by smallest mole. Divide through by smallest mole. So what is the smallest mole here? So the smallest mole here is obviously 0.031875. So divide, so 0.0063 divided by 0.031875. 0.19 divided by 0.031875. 0.031875 divided by 0.031875. all right, so now let's divide. So 0.063 divided by 0.031875. okay, so we'll be getting 1.97, which is approximately 2. We have to remember, we have to round it up to the nearest whole number. So then this one 0.19 divided by 0.031875. when we divide, we'll get 5.96, which is approximately 6. Why this one is 1? So the empirical formula is going to give us C2H6O. So this is the empirical formula. So now how do we calculate the molecular formula? Remember, molecular formula is equals to empirical formula N. So this will be C2H6O times N. N is what? Relative molecular mass divided by formula mass. Remember, relative molecular mass is going to be given to you in the question. What was it given? It was given as 92.16. So we say 92.16 divided by formula mass is the molar mass of your empirical formula. So how do you do? I will say 12 times 2 plus 1 times 6 plus 16. all right, so this will give us 92.16 divided by 24 plus 6 plus 16. 24 plus 6 is 30. 30 plus 16 will give us 46. all right, will give us 46. So this will be 92.16 divided by 46. So if we do that division, 92.16 divided by 46, this will give us 2. all right, so this is equal to 2. So it means that our molecular formula now will be equals to C2H6O 2. So these 2 will multiply into everything here. So we'll now have C4 2 times 6 12, then O2. all right, so that's our molecular formula. Okay, so now I want to just tell you a short statement. all right, now if you are calculating your empirical formula and you divide by the smallest mole and it's giving you something like, let's say, 1.5, okay, please don't round this up to 2. If it gives you 0.5, don't round it up to 1. If it gives you 2.5, don't round it up to to 3. If it's giving you 0.5, if it's giving you 0.5, multiply by 2. Multiply everything by 2. Even if it's only one value that is giving you 0.5, that is approximately 0.5, don't round it up to 2, or don't round it up to the nearest whole number. No. The only time you can round up is when it is very close to the whole number, like something like 1.8, 1.9, 1.7. Here you can round it up to 2. Something like 5.6, 5.8, 5, even 5.6 safe, you have to multiply. You have to multiply by 2, because 5.6 times 2. Look at it. 5.6 times 2. Are you seeing 11.2, which is approximately 11? That is the nearest whole number. So anything 0.6, 0.5, multiply by 2. Don't just round it up. Don't say 1.5 is 2. No, it's wrong. You don't apply those approximation methods here. You don't do that. You multiply through by 2, because the idea is that now that decimal, that 0.5 you're seeing here, every 0.5 has a decimal, has a fraction of 2. For instance, now 1.5 is what? 3/2. Are you seeing it? 2.5 is what? 5/2. They all have a denominator of 2. So multiply through by 2. So please, I want you to take note of this. All right, so like I've always been encouraging you, any question you find on empirical molecular formula, please do well to attempt it. Do well to try it out. All right, do well to try it out. So in the next live, I'll be ending this particular live class now. Okay, but in the next live class, we are going to be looking at mole concepts and stoichiometric calculations. Then after that, we'll look at the relationship between mole mass and of course particles, as well as Avogadro's number. Okay, then progressively we are going to be looking at limiting reagents and theoretical yields. Okay, and all of that. So see you in the next live class. All right, so do well to share this link to your colleagues. All right, so they can actually get to understand these concepts better. All right, so see you in the next live class.